In this video, we're going to start to talk about the different types of collisions and what is conserved in each type of collision. One thing to remember is that in all collisions, momentum is always conserved. And in the two different types of collisions that we're going to look at, inelastic and elastic collisions, we're going to look at the differences in the energy. When is energy conserved and when is energy not conserved? And so in an inelastic collision, kinetic energy is not conserved. So our momentum is conserved, but the kinetic energy is not. So the energy before the collision is not going to be the same as the energy after. However, the momentum before the collision is going to equal the momentum after. Some of the kinetic energy in an inelastic collision is converted into other types of energy, such as heat, sound, some work done on an object, or permanently to deform a particular object. When you think of collisions, the first thing you might think of are two cars hitting each other. And when a car hits another car, sometimes the cars themselves will get deformed, and that takes energy. And so that deformation is taking energy from the system and putting it into the environment. And so in that type of collision, kinetic energy is not conserved. However, momentum will be conserved. Now, in order to be perfectly inelastic in a collision, that's going to happen when the two objects stick together. And so when two objects collide and then they become one new object, if this happens, we classify that collision as perfectly inelastic. Not all of the kinetic energy is necessarily lost, but it's just not conserved. So there still will be energy after the collision, just some of that energy is transferred into other forms. The second type of collision that we're going to look at is an elastic collision. And in these collisions, both the momentum and the kinetic energy are conserved. So we can use the conservation of momentum equations where the initial momentum is equal to the final momentum, but we can also use the conservation of energy equations where the kinetic energy initially is going to equal the kinetic energy in the end after the collision. And this is when two objects hit and bounce off of each other. Typically, we'll have one object that's moving towards another object, and if they're both moving towards each other, then after the collision, they will be moving away from each other. Or another example, think of in billiards or in pool, when you have a ball and another ball is screaming towards it, and then it hits, and the first ball stays stationary where the second ball moves off with a velocity. These are examples of elastic collisions. Now, in true honesty, in the world that we live in, collisions are somewhere in between elastic collisions and perfectly inelastic collisions. Okay, it's rare to have a perfectly elastic collision where everything is conserved. Even in the pool ball scenario, there is sound, all right, and there's a tiny bit of friction in the interaction, but just to get that sound that we hear of the two balls hitting together, that takes energy. So some energy is lost. And in perfectly inelastic collisions, a lot of times there's going to be some deformation of one of the objects in order for those objects to stick. However, we are going to study the physics of these two types of collisions and seeing how things work on these extremes and knowing that everything else falls in between. Let's start by talking about a perfectly inelastic collision, and that's when two objects stick together after they collide. And we say that this is perfectly inelastic in that they become a new object. They each have their own mass before, and they each have their own independent velocities before. However, after the collision, they become one mass, which is the sum of the two masses, and they now have a collective velocity. So they're both moving at the same velocity in one particular direction. So our conservation of momentum becomes this equation here. Now, this is not a new equation. It's just simplifying the equation in this situation. It's still momentum before equals the momentum after. But in a perfectly inelastic collision, the momentum before, we have two different momentums, two separately independent momentums, and in the end we have one joint momentum where it's the sum of the two masses times the velocity that they're both moving collectively. One thing that we need to remember is that momentum is a vector quantity. And so momentum has a direction, not just a magnitude, and the direction is important. And be sure that we have the correct signs in all of our conventions. So the momentum before, make sure we know which one's positive, which one's negative. Are they both positive? Are they both negative? In the end, is the momentum positive or negative? And make sure we assign the appropriate signs. In elastic collisions, both the momentum and the kinetic energy are conserved, so we're going to have the two equations that we work with here in our conservation of momentum and conservation of energy. Now, because it's an elastic collision, the two objects are going to be independent of each other, and so we have the initial momentum of object 1, the initial momentum of object 2, and then we're going to have the final momentum of object 1 and the final momentum of object 2. Remember, momentum is a vector, so there are going to be signs here. They could be positive or negative momentum depending on the direction of the velocity. However, with the kinetic energy, once again, we are going to have separate kinetic energies, but energy is a scalar quantity, and so we don't need to worry about direction. We just look at the square of the velocity, and we look at the energy before is going to equal the energy after. So we're going to use these two equations, and we will solve them simultaneously depending on the information given or the information we need to find. In looking at these two equations, especially the conservation of energy equation, we can simplify it into this equation in seeing that the difference in the initial velocities is going to equal the opposite of the difference in the final velocities. And this is something that you will want to have on your formula card. And this is only for elastic collisions. And where does this come from? This comes from the conservation of kinetic energy, when the initial energy is equal to the final energy. To summarize the collisions, in an elastic collision, both momentum and kinetic energy are conserved. In inelastic collisions, only momentum is conserved and kinetic energy is not. And remember, that's not because of energy being transferred into other things such as sound, frictions, and deforming an object. In a perfectly inelastic collision, momentum is conserved, kinetic energy is not, and the two objects stick together and become a new object after the collision. So their final velocities are the same. When solving collision problems, it's important to set up a coordinate axis and define the velocities with respect to this axis. So which ones are positive, which ones are negative. It's often convenient to make your axis coincide with one of the initial velocities. So line up your positive x-axis in the direction of one of the velocities. Draw a diagram, and in your sketch, draw all the velocities vectors and label the velocities and their masses, both before and after the collision. With the conservation of momentum, write a general expression for the total momentum of the system before the collision, and write another expression for after the collision. Equate these two total momentum expressions, and then fill in all of your known values, allowing you to solve for your unknown. When you have an elastic collision and the energy is conserved, then you can say that the kinetic energy before the collision is equal to the kinetic energy after. Keep in mind, you can use that alternate equation looking at the difference of velocities, and that will help you at times, but sometimes you will have to rely back on the original kinetic energy equation. And remember, this only applies for perfectly elastic collisions. Solve the resulting equations simultaneously. As mentioned before, it is important to draw a sketch before and after the collisions, and so you have a picture of what's happening before, what's the direction of our velocities, and so therefore what's the direction of our momentum, and then draw a picture after so we can get the same information. Keep track of all the subscripts. There will be lots with a 1, 2, initial, and final, so be neat in your writing and make sure you understand what each quantity is. When you sketch a perfectly inelastic collision, the objects stick together, so include the velocities in the directions and understand that after the collision, the velocity will just be 1 and the masses will be combined, and they both move at the same velocity.